We are going to dissect the 28BYJ-48 stepper motor. This is a geared stepper motor, so in between the motor output shaft and the gearing output shaft we have a gear train that we'll look at later. There are 5 wires coming out of the motor. Since there is no feedback, these 5 wires are for the coils, the 2 coils, and that indicates that this motor is a unipolar stepper motor. So there are 2 windings per coil, and we'll look at that a little bit later too. So here's the motor, and we'll examine the operation of this motor and the gearing. Here is a dissected version, or one that's been opened, and we'll look first at the rotor. Here you can see the rotor. It has no visible teeth, which indicates that it's a permanent magnet stepper motor. And it's apparent when spinning the rotor that there's a small detent torque. So even though there's no current going through the windings, in fact there are no windings in it right now, there's some resistance to angular rotation, and that's the detent torque. So we can check and see how many different poles there are on this rotor by seeing how many clicks there are to rotate it. So if we just go through and get one full rotation, we count 16 clicks. So that means that there are 16 different stripes or sections of polarity on this rotor. And the cause for the detent torque is these metal projections, and the poles of the rotor are attracted to those metal projections, so there's a little bit of torque resisting motion. Now the coils that I've taken out, we have 2 coils for this permanent magnet stepper motor, and here's one coil and here's the other. So depending on the direction of current in those coils, they're going to have a different direction for magnetic field. So we could have a magnetic field oriented so that this side is north and this side is south. Now on the end of each of the coils there's this metal cap, and it has projections that go down and they interlock. So the projections from the opposite side are in between the projections on this side. So that means that the projections pointing up here, they'll have one polarity, and the projections coming down will have the other polarity. So when this is energized, these 2 different coils will have different polarity, and that's what interacts with the poles on the rotor to get the displacement that you want. So like I said, there are 2 coils, and you can see that for each coil there are 4 wires. There's 2 windings. So it's hard to see here, but I've zoomed in now and you can see that there are 2 windings per coil. So here's the wires for one winding, and here are the wires for the other winding. And those windings go in opposite directions. So if one of them is energized, the magnetic field will go one direction, and if the other winding is energized, then the magnetic field will have the opposite sense. And again, here's the coil that's normally on the top of the rotor, and you can put that metal plate there in order to have the projections for the different polarities that attract the rotor. So we'll look at a video of the windings being energized in an alternating sequence, and then see how that causes rotation in the stepper motor. Here's a picture on the gearing that we'll get to in a second. So real quick about this video, here is the stepper motor with the faceplate removed, and this 7-segment LED is used to illustrate or show the current going through each of the windings. So this set of 4 segments represents one of the coils. Oh really, I misspoke. This setup is made to drive 2 stepper motors. So this set of 4 LED segments represents the 4 windings on this stepper motor, and this shows the current and the windings for a stepper motor that's not shown. So we'll just look at the lights for one of these sets of 4. Again, there are 4 windings in the stepper motor, and we have 4 lights. So right now, the windings represented by these LEDs are energized, and that's brought the rotor into this position. And now let me play it for just a second. What we're going to do is change the polarity in the coil. So one coil is represented by opposite LEDs. So right now we have this winding of one of the coils energized and this winding is off, and for the other coil this winding is energized and this winding is off. So to get the rotor to step through, oh, by the way, this is called full step mode when both the coils are energized. So to get the rotor to take one full step, we're going to reverse the polarity of one of the coils. And since this is a unipolar design, we are going to de-energize one winding and energize the other winding in that coil. So we'll see that the rotor will move one step. And real quick, the step angle is given by the equation 360 degrees divided by the number of teeth in the rotor times the number of phases in the stator. So that's 360 divided by the product of 16 and 2, which gives you 11.25 degrees. So we should see the rotor move 11.25 degrees whenever we change the polarity of this coil. Okay, so we changed the polarity and the rotor moved. Changed the polarity of the next coil and the rotor took another step. So now the rotor should take one more step, and this coil will keep its polarity, but this coil will switch, so we'll go back to illuminated and turned off. Okay. So you can see we're just alternating back and forth the polarity of the coils, and that's causing the rotor to move through steps. Let's see. So you see that the rotor is moving in discrete steps of 11.25 degrees per step, and there are 32 steps for one revolution. Okay, and this is in full step mode. Now back to the motor. This is the gearing for this stepper motor. The motor's output shaft would come through this center hole here, and then it would be tied to the lower gear there, and then we have a gear train that goes all the way to the output shaft. And we'll look at the gear ratio and see what that is for this motor. So you can see that the input shaft for the motor is turning faster than would be turning faster than the output shaft. Now there's a web page where somebody has taken apart this motor and done a pretty good job documenting it, so we'll visit that page. There are 2 designs for this stepper motor. It has 2 different gear trains. This is the one that we're looking at here. So we've got the motor shaft and then 2 gears on this shaft, an idler gear, 2 on this one, and then the output shaft, which has a gear also. And the teeth are as follows. We have 9 teeth on the motor, which goes to a 32 tooth gear. And on that same shaft we have an 11 tooth gear, which goes to an idler. So the number of gears on that doesn't matter. We'll see that in a second mathematically. Then 16, and then on that shaft we have 10 going to a 31 tooth gear for the output shaft. So let's see what the gear ratio is for this motor. See the gear reduction on this stepper motor. Okay, I've drawn the directions for the different shafts. So here is, let's see if I can show those on the screen at the same time. So here is the motor shaft, and then I'll call this shaft B, shaft C, D, and E would be the output shaft. So both gears on this shaft have the same speed. So here's that omega B. So it's this shaft. So it has 2 gears on it. So then the idler would be C, shaft C, so that speed would be omega C. Then this should be shaft D, omega D, and omega E. So the definition of the gear ratio is the input speed divided by the output speed. And we'll just go through one shaft to the next in order to determine the output speed in terms of the input speed. So we have that speed B is motor speed times 9/32. So N1 divided by N2, so 9/32. And then omega C is omega B times 11/22. Omega D is omega C times 22/16. And finally, omega E is shaft speed D times 10/31. And then we can go back in substitutes for omega D. So we have omega C times 22/16 times 10/31. And then substitute for omega C. We end up with this. And then finally substitute for omega B and omega M. I'm sorry, for omega B. And so we have omega E in terms of omega M. And that gives us a gear ratio is just the product of the numerators divided by the product of the denominators. And you see that the 22 teeth of the idler cancel out. So the idler gear has no effect on the gear ratio. And this ends up being 16.032. So now back to the stepper motor. I'd said earlier that the step size is 11.25 degrees. And the gear ratio means that for each step of the motor, the output shaft turns 0.702 degrees. So there are 513.03 steps of the input signal per revolution of the output shaft.